Hi, everyone. My name's David. I'm a first-year grad student at the Center for Relativistic Astrophysics in Georgia Tech in Atlanta in the US. And I'm very excited to come today with some of our new recent performance calculations for the Trinity 1 telescope. This is an image of the first full Trinity 1 telescope. That it's an imaginary aeroshell telescope optimized for neutrino detection. And each Trinity site expects to consist of 6 of these telescopes. So let's point each one of these telescopes to a different question about Trinity that I will try to explain during this talk. And we'll start from here and move clockwise. So Trinity detects Earth-scheming neutrinos. And these are neutrinos that come at a very shallow angle. And then due to the charge current interaction, a tau lepton is produced. And due to the relativistic boost, this escapes the Earth. And when it decays, it generates a particle shower. And then we look at the chunk of light. So we focus this with a nearly spherical mirror that then focus light into a camera that is made of thousands of silicon PMs. And this is a technique that has been widely used by the gamma ray and cosmic ray community. So we have the advantage that the technology is well known. And it has actually been tried by the MAGIC collaboration to use their telescopes for neutrino detection, but they're not optimized for this. So then their sensitivity is pretty low. A single Trinity telescope is expected to be something like 15 MAGIC telescopes. And yeah, so we talk about a lot of neutrino observatories here. And a question that we get asked a lot is what's the difference from Trinity and other neutrino telescopes? And I think this is very well seen by looking at the diffuse flux sensitivities of different experiments. So as you can see, the ultra high energy part is mainly dominated by radio experiments, which sensitivity peaks at around this energy range. And then the low energy part is dominated by the ice and water Cherenkov telescopes like IceCube and TrimTrinet. And the main idea of Trinity is, well, the imaging technique actually serves to close this gap between these future planned and current telescopes. Another interesting fact is that our low energy tail actually overlaps with IceCube. So this ensures that we will see neutrino events with a full Trinity array. Another thing that we have is as an imaginary Cherenkov telescope that we point downwards, then we basically have no background because the background that one will expect in this type of telescopes comes from gamma rays and cosmic ray showers. So since neutrinos are upward showers and the other showers are downward, we expect no background. And we have a very good angular resolution and very deep sensitivity, which makes us an ideal experiment for point source searches, which we all know that it's a thing that we're all trying to do in the community. And in general, we just prove the imaging technique as a valid method for ultra high energy neutrino searches. So what have we done? Where are we now and where are we going with Trinity? So far, we have what we call the Trinity demonstrator, which is a 1 square meter telescope with a 4 × 4 degree field of view. And the main objective of the telescope is to test the remote operations, test the camera, and study the background. You will listen more about the demonstrator in Sophia's talk right next to me. And we have been taking data since 2023 that right now we're starting to analyze. We have, you'll see more of this in Sophia's talk. And then we have the Trinity 1 telescope, which is a telescope that's 16 times bigger. As I said, optimized for neutrino detection, wide field of view so that you cover a big portion of the Earth, which makes a very big fiducial volume for neutrino interactions. And we expect around a 0.3 degree angular resolution from the camera. And we are currently looking for funding. We're expecting to get something by next year, but that could be later due to the current situation. And then 5 years after our first telescope, we expect to get the funding or start building the full site telescope, which will consist of 3 sites with 6 telescopes each. And basically, the diffuse flux sensitivity increases linearly with the number of telescopes. So this is why you see about like an order of magnitude increase in linear sensitivity from 1 telescope to the full 18 telescope array. And another question that I want to address is what's our capabilities from detection? And for that, I have our effective area. So here you can see our effective area for tau neutrinos of 10 to the 6 GeVs and 10 to the 9 GeVs. And the effective area calculations are done with new tau sim and Corsica simulations. This is used for parametrization, and then we do some semi-analytical calculations as well. But something interesting to look at here is if we zoom in a little, we can see how the band gets a bit narrower, and this is mainly because the increase in the neutrino cross-section once one goes to higher energies. So we basically can mostly observe neutrinos coming from more shallow angles or very close to the horizon. That's why we point our telescope to the horizon. And another good thing about Trinity is that we plan to be able to rotate in azimuth so that we have a sky coverage once we rotate in azimuth from what is shown here in the picture. And then we use this quantity that we call acceptance, which is basically our integrated effective area with an e⁻² spectrum, integrated over the time as well, because one of the downsides of Trinity is that we don't have a 100% duty cycle, because we can only observe at night and only under certain illumination conditions. So then this is all taken into account in this calculation. So we did this so that people can have an idea of the response from an e⁻² spectrum after 1 year and after 1 day here, for example. And when we run the calculations, it turns out that we have around a 20% duty cycle of the year, which is everything already included in the acceptance plots. So now, of course, we think of what is our science case and what can we actually do with Trinity. And we've been talking a lot about blazar flares here, and that's one of the things that we thought of first. So in the US, we call this Texas. For this, I actually took this image from a paper by Maria, and we used this SED from Texas as a bit of like a benchmark flux to just have the spectral shape of the phototronic production mechanism, and then some normalization that's up to the level of the IceCube data for the 2014 flare. And with this, we calculate how many events we would have expected from an event like this. And we use our direction average effective area and the operation time, where we consider our 20% duty cycle. And we see that our number of expected events for a flare like the 2014 one from Texas is around 1.2 events, more or less. And then at around 400 megaparsec for a flaring time of around 158 days, just like Texas, we would expect more than 10 events. And I think one of our big science cases would be GRB physics. And I think we can very well see this by looking at our short burst sensitivity. And here I'm showing the Trinity 1 short burst sensitivity, so a single Trinity telescope, and then some GRB models for high luminosity GRBs. This is in particular for a bolt-like GRB, so very high energetics, and a short GRB that are related to binary neutron star mergers that we were just talking about. And what you can see is, first of all, that our sensitivity with one telescope, it's already comparable to 100 stations for Beacon, which is a radio telescope. And the other one is that our energy range is ideal for the GRB models that we have right now. So we expect that if we, get kind of lucky and we see a couple sources, we should be able to place constraints at least, or even if we have a highly energetic source that's close enough, we could even rule out models. From this, we actually calculate like how many events we expect from a bolt-like GRB, considering the internal shock model. And for a 10 gigaparsec source, we see that for our maximum effective area, we have something like 61 events. And then from this, we calculate what's the Poisson probability of detection if the source falls within our field of view. And we can see that for these bolt-like GRBs, for these two different models, at around 10 gigaparsec, we have almost a 100% probability of detection. We did the calculation as well for the extended emission of short GRBs. And here we can see that we have a maximum number of events of around 26. And at around 100 megaparsec, we still have around an 80% probability of detection. This is detecting at least one neutrino event from the source, the Poisson probability. But of course, the event has to fall within our field of view. So this is where the repointing comes into place. Because at least with short GRBs, we would expect to be able to come to follow up on gravitational wave events. So if we follow gravitational wave triggers that, for example, the ICEM telescope expects something around a couple hundred events per year, then we have all of this accessible sky that we should see. And then we use this instantaneous accessible sky with our effective areas. And we try to compute how long would it take for Trinity 1 to actually look at least one neutrino from short GRB. And we get to 100% in 10 years. And we get to around 60% in 2 years and 80% in 6 years. Again, this is only a single Trinity telescope. Of course, your field of view increases a lot when you consider the full array. So like a 63% probability goes to around 99% when we calculate with the full Trinity telescope. And this is, of course, work in progress. So stay tuned. We hope to be able to have something finished for publication around this year, I hope. And if you're going to ICRC, you can go and check out our proceeding on Trinity 1 there. And stay tuned for some of the data analysis from our first Trinity demonstrator data run from Sophia right next. And this is my first talk as a graduate student, so I would really appreciate feedback from people. So I have a little survey if you take some time to fill that, and I'll be happy to take any questions.
Thank you, David. Are there any questions?
So first feedback, great talk, very nice
Thank you.
slides. You mentioned for the full Trinity 3 sites. How do I have to imagine this? Is this on the same mountaintop or?
So yeah, it's in a mountaintop,
Yeah.
and then you expect to put it on a mountaintop that's about like unobstructed in the surroundings, so that you put like 6 60-degree field of view telescopes, and then you cover the whole 360-degree field of view.
Okay,
Yes.
thanks.
Have you thought about neutrinos interacting with the mountain? Because in Oyer, I did a project on that, and like it actually, the Earth skimming neutrinos, you can also
with
detect,
the mountain that we're in.
yeah, you can also detect neutrinos that interact with the Andes. In that case, I don't know if.
So, I mean, we're focusing the light with the mirrors into the camera. So if we have a neutrino coming from the actual mountain, there's no space for the shower to develop.
Okay.
So I don't think we would be able to see any of that.
The pointing is very restricted because it's based on a Cherenkov telescope. So my question is, if you're expecting to be sensitive to GRBs, how long have you measured? Have you compared, like for example, with MAGIC, how much time would it take for pointing to like follow up on, let's say, gravitational wave observation or something?
Yeah. So MAGIC, I think they're like at something like 20 seconds. So that's a very good point, because I mean, the thing is, from gravitational wave events, we don't know what's the time delay between the gravitational wave trigger and the neutrino emission. So that's why we talk about gravitational wave events and not electromagnetic follow-ups. But we could also just do electromagnetic follow-ups. But then the electromagnetic trigger takes a while. And then if we take around 20 seconds to move our telescope and we're looking at a 100-second emission, that might be complicated. But
yeah, but that's kind of my question, because if it's short GRBs, then the time scale is very small, and it might be comparable to like the repointing.
Yeah, I mean, so the goal is to do a repointing in, I would say, something around 20 seconds.
Okay.
Yeah, something like that. I don't know if that's a question.
Yeah.
Okay. Yeah.